Um, Hello, everyone. Welcome to today's lesson. Today, we are going to talk about how we can estimate and actually predict the stress, the stress increase from the loads that we place on the soil ground. So if we put some loads on the ground surface, what it's going to do is it's going to increase the stress that the soil element feels, and it may shrink or expand in the horizontal direction. These deformations can cause a problem. So if we have underground substructures, so engineers need to be able to estimate the induced stresses in the soil and evaluate its effect on the substructures. The engineers would like to use the stresses based on elastic theory because they are closed forms solutions. That means we can get a very simple equation that you can just program into a spreadsheet or a MATLAB program. These solutions tend to be conservative for most cases, meaning they are not going to underpredict the stresses. Now let's look at the Boussinesq solution. So Boussinesq was a French mathematician and physicist. He used the elastic methods to derive a full series of equations that would estimate the stresses or induced stresses in the X, Y, and Z direction on a soil element from the different type of loads placed on the ground surface. So it assumes the soil is isotropic, homogeneous, and the soil is elastic. So now this particular solution I'm showing you is for a point load. So we have a point load acting on the ground surface. We know this will extend out at a certain radius. Can just anyone who join in just try to mute yourself? So we know this will extend out at a certain radius and affect the ground at some particular depth. So Boussinesq equation could calculate the stress increase at any point A. So if you have a point load active, so this P is acting on a point on the ground. So either the point A is here, or you have another point A, or another point A prime, anywhere beneath the ground. We have the solution to calculate the stress increase at that point. So the solution, this is the solution, the stress increase only in the vertical direction. So this tends to be one we cared about the most. The stress increase is a function of the radial distance R, but not for the soil property, because we only see there's a term, the component, the term P, and Z, that's the coordinate. So the Z coordinate of the point A. We haven't seen the Young's modulus or Poisson's ratio in this formula. So which means it doesn't matter what type of soil I have. So whether it's clay, sand, or gravel, silt, or organics, we come up with the same stress increase. So in other words, the soil type does not matter when we talk about Boussinesq method. So one of the advantage is that, of course, I really don't need to know anything about actual soil conditions to estimate what the induced stress would be from the load I'm applying to the ground surface. So for this Boussinesq equation, this third represents the increase in the particular quantity due to applied load in the distance R. And this R, that's the radial distance measured from the point of the applied load to your current, the point you are interested, and is expressed as the square root of x squared plus y squared plus z squared. We also have an expression for the total stress increase in the x, y, and z direction. So that's the final expression for the stress increase in the three directions. So actually this figure, that's just only the side view. So you have the X coordinate, Y coordinate. Actually, there's a X coordinate and Z coordinate. So there's Y coordinate or Y direction as well. And this Y direction, that's into the page. So that's the direction into the page. So we have to have the stress increase in the Y direction as well. And Boussinesq also developed a formula to calculate the displacement in the Z direction. So ΔUZ due to the applied load. So it's a function of the applied force P. Applied force P, the soil property, the Young's modulus E, and Poisson's ratio mu. And also as well as the location of the point. So if the location is confirmed, then you know the Z coordinate. You also will know the radius R. So that's how you are able to calculate the vertical displacement. So the solution for this point load is important because it can be used to develop the solutions for distributed load through the process of integration. So this one just only the point load. So how about for the circular load? So if the solution for the point load is integrated over a circular area, then the solution of the stress increase at this point A, which is directly below the center of the circular load. So that will be the, if you do the projection, that's the center of this circular load. That could be obtained and expressed as this simple analytical solution. So, and within this solution, the A, that's the radius of the circular loading. So that's the radius of the circular loading. And the Q, that's the uniform loading. So Q, that's the surcharge, uniform surcharge on this circular area. And the Z, that's the depth of point A. So that's the vertical coordinate of this point A. So this is only for stress increase at point A, which is below the center of the circular loading. So if you have a circular loading, so that this circular loading, actually you do the integration. So actually that's a sum of the previous line load or point load. That's the sum of the previous point load. Then you get, if your loading area, that's a circular area, then that's you can come up this analytical solution. And any point, so this is center. So if you do the projection, so any point below this center point, you're able to use this analytical solution to calculate the stress increase. So if this is a point A, so you are able to calculate the delta sigma ZZ. So that will be the stress increase at this point if you apply a circular load on top of the soil ground. So this is one scenario. So on the other hand, how about, let's say my point, the point I interest, that's somewhere not below the center line, is point B here or point B prime over here. How we are going to calculate the stress increase. So we have another method. So this is the point B. If the point B, that's not directly below the center line, then we are able to use the design chart to find the influence coefficient I sigma. So here we introduce one parameter, it's called I sigma. So that's the so-called the influence coefficient. And if this influence coefficient times the surcharge Q gives you the stress increase, and any point B is not below the center line of the circular loading. So for this design chart, if we look at the vertical axis, so this is the Z over A. So that's the ratio of Z over A. And this Z, that's the vertical coordinate of the point B. So that's Z. And this A, that's the radius of the circular loading. So once you know the position of the point B, then you should be able to get the ratio Z over A. And those curved lines, that's the ratio of R over A. So, and this R, that's the distance between the point B and point A. So if point B is here, then you just draw a horizontal line to this corresponding line that lies in the center line below the circular loading. So that will be R as well. So R over A, you are able to get the ratio, and the magnitude is labeled on this chart. So once you get J and A, so let's say if R over A is 7, let's say it's that 7, then obviously it's here. It's this line, R over A is 7. And then you are able to find J over A, let's say if it's 4, then you are able to find intersection point here. Then you just draw a vertical line and intersect with the top horizontal axis. It gives you the influence coefficient. So that's 3 times 10 to the power of -3. So that's the corresponding influence coefficient. So that's how we find the value from this design chart. And once you get I sigma times Q, it gives us the stress increase at any point B. That's not lies on this center line. So that's 2 scenarios. For circular loading, we have 2 scenarios. Now let's just look at just one example. So for circular loading, so here we have a surface loading Q equal to 100 kPa, acting on circular area with a diameter of 5 meters. So we know the D and we will know the A as well. The point A, that's 2 meters below the soil surface, is here. And point B, that's 5 meters away from the point A. So we are required to calculate the vertical stress increase at point A and B. So for the circular loading and any point below the center A, we are able to use this analytical solution to calculate stress increase. So now the Q, that's 100 kPa. And because the radius, that's 5, and A, that's the diameter, that's 5 meters. So the radius A will be 2.5 meters. And J, that's the vertical coordinate of the point A. So J, that's equals to 2. So if we plug in all 3 values into this formula, we're able to easily work out the stress increase of point A, which is 75.6 kPa. 75.6 kPa. So if we follow the same way, if you are required to calculate any point here, any point, another point here, or another point here, then once you find that A and J, and also the Q, then you are able to calculate the sigma JJ directly. So now for the point B, because it's not directly below the center of the circular loading, so we have to use this design chart. So now the vertical axis, J over A. So J over A, we know that J is 2, so that's given in the figure. And A, that's 2.5 meters, that's the radius. So the ratio, we get J over A, that's 0.8. So where is 0.8? So it's roughly, so that's 1. So 0.8 should be somewhere here. And R over A, J over A should be somewhere here. So that's 2, that's 1, that's roughly 0.8, roughly here. So R over A, that's the R here, that's the R. So R, that's 5 meters. And A, again, that's the radius of the circular loading. So that's 2.5. So we get a ratio of 2. So that's the R over A line. It's here. Now we just draw the. So J over A, we know is roughly here. So because that's 1, you see, that's 1. That's 1.
Excuse me, sir.
Yeah.
So R over A is always gonna be 2 because it's the radius divided by this half.
Yeah, that's 2. So that's R. R is here, this one. And radius, that's the radius circle loading. So that's 2.5. So 5 divided by 2.5.
But if even if the radius is 4 meter of any other meter, it's still gonna be 2 because the A is the half of the R, isn't it?
Yeah.
So it's gonna be always R gonna be R over A always gonna be 2.
No. This one, you see that you see if B is here, if B that's 10 meters away, then it will be 4. So B is the distance. You see B is the distance to the any point in this horizontal line, but directly below the center of the loading. So let's say if you are required to calculate B here, then you just draw a horizontal line and intersect with this vertical line, and then you find the horizontal distance. So that's the R. So that's R. Okay. So that will be 10 meters. So 10,
okay.
Yeah. So that'll be fine.
Thank you.
Yeah. So
sir, how are we gonna find the number we need from the graph?
So you see, I just show you one example. You see, you just highlight this R over A on the chart. So obviously this is R over A line because that's 2. And then you find the vertical axis, J over A, that's 0.8. You are able to label here. Then you draw a horizontal line. A intersect will be somewhere here. Then you just draw a vertical line, intersect with the horizontal axis. So that gives you the value. So this one roughly 3 times 10 to the power of -2. So that's 0.03. So that's the influence coefficient. So you just calculate Z R over A and just highlight that figure. Then you'll find the corresponding Z over A and then draw horizontal line. It will intersect with this R over A line with a point. Then through this point, you draw a vertical line. It will intersect with the horizontal axis. Then you'll take the reading. That gives you the I sigma. So for this case, the I sigma, that's 0.03. So I sigma times Q gives you the stress increase. So 0.03 times 100. Because the Q, that's 100. So that's how we calculate the stress increase. There's 3 kPa at the point B. So similarly, you are able to calculate any other point, capital B here as well. So only this A, once the circular area that's provided, so this A will be constant, but this R, that's the radius. So that varies with the distance to this line, to this vertical line. Okay. So that's for the circular loading, and also for any point below the center line, or any point that's external to this center line.
So the Q is the loading of the circle loading. The Q is the loading.
Yeah, Q is the uniform load or so-called surcharge. So you see, so if you put maybe a circular object on top of ground, so that will be that will apply some uniform pressure on the ground. So that's the Q. So that's Q. So normally that will be provided in the question. Yeah. So previous case, that's only for the, so now by now we have learned the point load and also the circular loading. But in the real scenarios, many loading situations, they occurring in practice. They consist of a number of rectangular regions. So actually this part, that's really important. So we have to be careful about the rectangular loading. So it is of interest to be able to calculate the vertical stress increase due to uniformly distributed load acting on a rectangular loaded area. So this is shown schematically in this figure. So we have a rectangular area and it's all uniform load acting. Actually, it's just like this. If 3-dimensional view, it will be like this. So you have a rectangular area and uniform load acting in this area. And we are interested to calculate the point O. So that's the Z meter So that's Z below, in terms of Z meter, below the ground, and it's also at one corner of this rectangular load. And also this, we have a rectangular loading area with the length of L and width of B. So point O, that's directly below the center of the rectangular loaded area. So vertical stress increase sigma ZZ from point O, which is one corner of the rectangular load, is still calculated as sigma times Q, So this time we need to select the influence coefficient as sigma from another design chart. It's called Fidem's design chart, but actually it's quite similar. So the way we pick up the influence coefficient is quite similar. So if we look at the chart, the horizontal axis is N. So it's the ratio of L over Z. And the curves on the chart now goes to M, so which is the ratio of B over Z. So L and B, that's the length and width of the circular loading area. And Z, that's the depth of the point. So actually L is always, or for the majority of the case, is always the long side of the rectangle. So that's the long side of the rectangle. And B, that's the always the short side of the rectangle. Yeah.
So they in meters, like
which one?
The length and breadth, don't know.
No, you see, it's like.
Or like to what units are they in?
No, you see, this is just like a representation. So it can be meter or centimeter.
Oh, okay.
So it varies with question.
It doesn't quite matter. Yeah.
Yeah, but you have to be consistent with the unit. So if here is meter, then say you have to be meter as well. Otherwise, eventually you have to work out the ratio. So you have to maintain the same unit.
Yeah, sweet. Thank you.
Yeah. So, so you just match up.
Sorry, sir.
Yeah.
Like over here, right? We have an equation where it's like M equals to L over Z, and then N equals to B over Z. But then the chart over here says N equals to L over Z, and then M equals to B over Z.
That's a good question. Maybe I will just cover this in 1 minute. So you just watch up your computed M and N and go to the appropriate line and interpolate your value for your influence factor. So because we know that here, you see, this is important. So M and N are interchangeable. So M equal to L over Z, N equal to B over Z. So you can also do the reverse way. So if N equal to L over Z and here M equal to B over Z, your result will be the same. So later on, it's maybe a bit not easy to understand, but later on I will show you one example why that's the case. So it doesn't matter whether just N equal to L over Z or M equal to L over Z, but your final influence coefficient will be the same from the chart. Later on I will show you with one example why that's the case. So, well, I want to emphasize right now, this is below the corner. We need to calculate the stress increase below the corner, not the center. So if it's center, then this way it doesn't work. So we have to be careful. Although the chart gives the stress increase directly below one of the corners of a rectangular loading, it can, however, be used to construct the value of the stress increase at any point in the elastic area. Now let's have a look at such situations. Do you have me to erase those ones? Those shapes?
Yeah.
Okay. So this chart actually shows us the different scenarios of vertical stress increase at any point below the rectangular loading area. So in total, we have six cases from the case 1 to case 6. So the red dot represent the point at which the pressure or the stress increase at depth Z that's required. So actually, Z is somewhere below the ground, but we just project that Z point upward to this point A. So it's aligned with point A. So it's the same case for the other scenarios. So for the first case, the point it at one corner, so we can work out the stress increase straight away according to that Fidem's design chart. Case 2, the point is at the center of the rectangle. But be aware of that for using the Fidem design chart, this point has to be one corner of the rectangle. So we have to split this big rectangle into 4 small rectangles. So this point will be the corner of each small rectangle. And then once we calculate stress increase for 4 small rectangles, then you are able to add all 4 values together. That gives you the stress increase for the center of the rectangle. And similarly, for case 3, at this point, the red dot, that's not in the center of rectangle. So we were able to break the shape into 4 small rectangles and then calculate the stress increase separately and add them together. And case 4, so we are able to break it into 2 rectangles. And case 5, again, that's 2 rectangles. So that's the easy case. And case 6, the red dot, so that's outside the loading area. So we have to make a big rectangle and 3 small rectangles. So one big rectangle, so AIEG. So that's one big rectangle. So that's one rectangular loading. We just do one calculation. But because we over-considered the loading area, the actual loading area is just here. So we have to minus the loading area for the BEHG. And but this one, we over-accounted as well. So we have to minus the loading area, the loading or the stress increase for this rectangular loading area. But we over-minus this small area. So we have to plus the stress increase for this small rectangle, CF and GH. So that's how we just construct the rectangles and do the calculation. So anyway, for all the cases, you have to make sure the point you are trying to calculate, it becomes the corner of the rectangle and it shares between all the shapes that you split or you constructed. So you see, let's say this dot was shared by all 4 rectangles. And this one, the red dot, that's all shared by 4 rectangles. So that's 1, 2, 3, 4. And this one, that's the same case. So you have to make sure this point that's falls in the corner of all the rectangles. That's really important. It can be in the center of the rectangle.
So case 2, right? We find the stress of A, B, C, D, and then we times it by 4.
Yeah, no. This is not 4. This one you can times 4 because you see the loading area is the same. But this one you have to calculate separately.
Oh yeah.
The loading area different. So this one. So actually, the case 3 and case 4, that's a really important case because all the other cases, case 1, 2, 1, 2, 4, 6, that's very simple. So you are able to calculate only add one case, that's it, or times 2, or times 4, that's it. But case 3 and case 4, all the shape, the loading area are different. So you have to calculate separately and just do mathematical calculation later on.
Yeah,
wouldn't case 6 be negative?
This one?
Case 6, yeah.
Yeah.
Wouldn't it be negative?
What do you mean negative?
Well, yeah, you're minusing.
No, it won't be negative because eventually you see if this one minus those two rectangle and plus this one, eventually we just get a value for this area. So surely it won't be a negative. It will be positive all the time. So later on, I will show you two examples. One cover for this case, and the other one for cover case 6 for us to have a better understanding. So one just any point is not center, it's inside this rectangle loading, but it's not in the center. It's not in the lamb's symmetry. And the other one, the point outside the rectangular loading, okay?
Yeah, understood.
Yeah. Now we just look at one example. So you see, this is one example to calculate the stress increase below an interior point of loaded area. So actually, this belongs to case 3. So it means, so if I make drawings, so that will be the rectangular loading. So rectangular loading, you have the Q act, so that's the ground surface, and you have a point O, and point O is somewhere here. So if you do the projection, so that's the point O, that is J meter below J, so it's J below the ground. So that's the scenario. We are required to calculate the stress increase at point O. And if you do the vertical projection, so it's in somewhere here, inside the center. So at point O, the stress increase will be calculated as the stress increase for those 4 rectangles. So we draw the vertical line and horizontal line through the point O. We break this rectangle into 4 small rectangles. So the total stress increase equal to stress increase for OXAY. OXAY, that's this one. And stress increase OYBZ. So that's a stress increase for this area. And OJCT, that's this part. And OTDX. Okay, so now this example is to calculate the stress increase at depths of 2 meters. So J is provided. So that's 2 meters between below the point O due to the rectangular loading ABCD as shown in this figure. So obviously we need to break it into 4 rectangles and calculate the stress increase separately and then add them together. So now we just do it one by one. So for rectangular loading OJCT, we have the M equal to, so M is, so this time the L will be the longer side of this small rectangle. So since this is a square, so it doesn't matter which one is which. So, but here, so L is 2 meters or B equal to meter, doesn't matter. Because here that's a 2 meters, that's 2 meters. So M equal to L over Z, so that's 2 divided by 2. Z, that's constant, because Z, that's 2 meters below the circle, below the ground, that's already provided. So we are able to get the ratio of M equal to 1 and N equal to 1. And then we start to find the influence coefficient from this Pfeider's design chart. So M equal to 1 or N equal to 1. Maybe we start from horizontal axis. N equal to 1, so obviously it's this line. So N equal to 1. And then M equal to 1, we just find M equal to 1. The line represents M equal to 1. So that's 0.2, 0.3, 4, 5, 6, 7, 8, 9, 10. So this is M equal to 1. So it's labeled on the chart. So obviously here you have one intersection point. Then you just draw the horizontal line, the corresponding value on the vertical axis. That's the influence coefficient and sigma. So just a bit difference. The value should be similar. So that's 0.175. So it's here, somewhere here. So that's how we pick up the value of influence coefficient. So I sigma times Q. So that's I sigma times Q gives us their sigma ZZ. So 0.175 times 100, that's given in the question. So the stress increase for this rectangular area, OZCT, that's 17.5 kPa. So that's the first rectangle. And then how about the second one? So for rectangular loading, OT dx.
Okay, so why is Q 100?
The 100 that's provided. So you have the rectangular surcharge Q, that's 100 kPa, that's provided in the question.
Wait, are you sure? Because like I can't see it.
Maybe it's missing. It should be the Q equal to 100.
Oh, okay.
Somewhere, yeah.
Thank you.
Yeah, that's a good question. So maybe I add later on, Q equal to 100.
Yeah.
How about for the second case? M equal to, so this time, because it's a rectangle, it's no longer a square. So we take the longer length as L. So this is L, that's 3 meter. And this is the shorter length. So that's a B equal to 2 meter. And Z, again, that's 2 meter. So M equal to L over Z, that's 1.5. And N equal to B over Z, so that's 1. So now from the chart, so N equal to 1, we draw, so that's N equal to 1, we draw the vertical line. And M equal to 1.5. So that's 1, that's the value 1, that's roughly 1.5. So we take the value from the vertical axis. So that's the raw value of 0.194. So previously I mentioned, you see M and N are interchangeable. So how about this time I just do the reverse way to see whether I get the same influence coefficient. So this time N, I make N as 1.5. So N 1.5. So obviously this is 1 because that's in the log scale. So that will be 2. So N equal to 1.5. That should be somewhere here. M equal to 1.5 and N equal to 1. So I draw the vertical line. This is not a vertical line, that's a curvy line. So I draw a vertical line, 1.5. And I find intersect with the N. If M is 1.5, then N equal to 1, right? So that's N equal to 1 line here, you see? And then I draw the corresponding horizontal line. You see, it aligns with this one. So you end up the same influence coefficient. That's why I'm saying the M and N are interchangeable. So if you get the ratio 1.5 and 1, either is M equal to 1.5, N equal to 1, or M equal to 1, N equals 1.5. You end up with the same influence coefficient. So again, this I sigma times Q gives us the stress increase for this rectangular loading area, OT dx. So that's 19.4 kPa. So again, similarly for the rectangular loading area, or X, AY, so we calculate the M and the N. So this one is the same as the last one, right? Oh no, the ratio is different because because the B is different. So M is the ratio of L over Z. So that's 1.5. So that's here, that's 3 meter. Here, that's 3 meter. So actually that's a square. That's a square. So M equals 1.5. N equals 1.5. And so 1.5 is here and 1.5. So we are able to pick up the I sigma from the Feder's design chart. And here, that's our final value for the stress increase for OSAY. And finally, for the rectangular loading OYBZ. So that now this time the L, that's 3 meter. So N, B, that's 2 meter. So m equal to 3 divided by 2, that's 1.5, and n, that's 1. So again, we're able to pick out the influence coefficient is this value, and that's our stress increase for this loading area. So by now, since we got the stress increase for all 4 small rectangles, now we are able to add them together. So if we add all 4 values, then we came out the stress increase for this circular loading. And at point O, which is 2 for this rectangular loading, and 4.0, which is 2 meters below the loading area. Any questions for this one? So this case was case 3. So there's 1 point in the internal area of the rectangular loading.
I'm not sure which line you're actually following, because in one you were on the one above and then the other one was below. Can you just explain that part?
Which one? This
which line you're actually following?
So you see this firstly, I found the n equal to 1, right? This is no problem, right?
Yeah.
So n equal to 1, and then you just draw a vertical line. You can draw a vertical line through to the vertical axis, and then you find the m equal to 1.5. M equal to 1.5. So this one m equal to 5.5 because it's quite crowded. So it should be this line. You see. I think maybe in your assessment, you will be provided with another chart. That's why it has a clear label on the chart. So you can more easy to find which line corresponds to which. This one maybe looks a bit tricky to find the value. But this one, there's m equal to 1.5. So that's why you have the intersection point here. And you draw the horizontal. Yeah.
Sorry to say, but all these graphs, they are not clear. Like even this and the others, like they are a bit like this one is very hard to find the exact value on them.
Which one? You mean this finder design chart?
Yeah, even this chart and the other, like the soils and like different soil type, and like almost all the charts, they are not clear.
Why this one not clear?
No, this is fine. The concept is clear. No, but when you get the value from the 2 parameters, like it's hard to find on exactly where to get the chart value, because
no, just like I said, you see this one won't be provided in your assessment. You'll be provided with another one. That's one I think I already provided in the formula sheet. So that's a summary of all the important formulas in the for this class. So that will be another clear one. That's why you see you have a clear label. Let's say this one, you see 0.8, and this one, that's 1. And this one, 2.0. Yeah. So that's one you easily know which one.
It's hard to find I stress. Like he's saying that it's hard to find the value here exactly. Like it's hard to find that exact value because of the chart label.
Yeah,
even 1.5 or 1.1, which line is representing is hard to say because.
Yeah. So you see this one here, that will be 0.0. So you can count upward. You see 0.1, 1, 2, 3, 4, 5. This one will be 0.05, and this one will be 0.1, and this one will be 0.15.
It wouldn't matter.
Well, anyway, I think this chart won't be used in any assessment. This is just for some demonstration for this lecture. You will be provided with another chart, like I mentioned.
It wouldn't matter if you wrote 19.5, for example, instead of 4.
19.4, which one?
Where you've got 19.4. If you wrote 19.5.
Yeah, this one, that's fine. That's fine.
Wouldn't make any difference, would it?
Yeah. So because here, because of your own judgment was involved, so such human error that's unavoidable. So you are able to, so this one that's allowable. But as long as it's not crazy difference, then that's fine. So let's say if I get a value of 0.197, then that's fine. But maybe later on by the end of the lecture, if I have time, I will show you another chart. So that's one will be mainly used for the calculation. This one, I agree, is a bit, it's very messy, but this one just only for demonstration. So that's one, you have a clear label for the vertical axis and also for the each line, okay? Like this way. So if you're not away by the end of lecture, I will show you that design chart. Okay?
Yeah, that's fine. Thank you.
Okay. Maybe I just label it. So let's continue. So how about the stress increase below the exterior point of loaded area, which is the case 6? Can you just help me to remove this one, the marker? So this time, the stress increase myself. So this time the stress increase for the point O, but only for this vertical, for this loading ABCD area. So that will be equals to OXAY and plus OZCT and minus OZBY and minus OXDT. So this one we already discussed before. So if we look further, so who just left this one marker here? Can you just remove that one? Thank you. So if we look further, we have 4 steps. So again, that's the previous case. So if we look further, so step 1 is actually we just, because of the O, that's the outside this loading area. So but we have to form a rectangle to make this point O as a corner. So we just form this big rectangle and we apply the Q to all the area OXAY. So that's the first step. And then second step is because later on we have to minus the loading area, this loading area and this loading area. So we minus this part twice. So we have to add it right now. So we add the loading over the OZCT. So originally that's Q. If we add another Q, that becomes 2Q. And now we start to just take or unload the Q. So from OZBY from this shape. So this one, right now that's 2Q and that's Q. So 2Q minus Q, that gives us the Q. And this one, Q minus Q. So here no longer have loading at all. And then if we continue to do the unloading for this part from the OXAT or OXDT on this part. So that's the original one. If you continue unload, so this Q minus Q gives 0. And this Q minus Q, that gives you 0. So eventually, if you do follow those 4 steps, so your Q, so that's your real loading area, but you are still able to calculate, get the stress increase for point O. So that's the explanation. So the again, that will be the expression for the final stress increase for the shape ABCD.
Yes, could you explain it again, please?
So you see, originally we have the loading area ABCD, right? Only ABCD.
Yep.
So yeah, only ABCD. So now because ABCD, because the point O, that's not inside this loading area, that's outside this loading area. But if we would like to use this rectangular folder design chart, then this O has to be one corner of the rectangular loading area. So we form a big rectangle and we assume the Q is applied through this big rectangle, So you have Q for these 4 rectangles, 4 small rectangles. Is that clear?
Yep.
So you have load through those 4 rectangles. But later on, because later on you have to minus the rectangle, this rectangle, this shape, and this shape. So, which means you just minus this small rectangle twice because that's overlapping between those two shapes. So you have to add that one. So I just temporarily add the rectangular loading of Q in this area. So it becomes 2Q. Is that clear?
Sorry, 1 second. O, X, A, Y.
So you originally you just apply to the big loading area, but eventually you have to come up to only this rectangular loading area, A, B, C, D. So you have a big one, but actually you over account the area. So this area you over account, and this area you over account, right? So you have to try to minus this rectangular shape and this rectangular shape. But you minus this part twice. Otherwise, here will be negative Q. So you have to add 1 Q here, small rectangular loading area. So that's why I add 1 Q loading area, OZCT here. Okay, so the Q becomes 2Q. And then next time, the step 3, you just minus this rectangle. So the 2Q, this is 2Q, this is Q. So 2Q minus Q, and this is Q minus Q. So Q minus Q, here you no longer have loading. And this 2Q minus Q, it becomes Q. So now you just minus this rectangular loading. So next we minus another rectangular loading on the top. So Q minus Q equal to 0, here becomes 0. And this Q minus Q, it becomes 0 as well. So we only have this Q and it's the original area, the real loading area is actually. And in this way, we are also able to calculate the stress increase because point O, that's the corner point of all 4 rectangles.
So what I can see in the formula is you've added up the total square, and then you've taken out the small, you've added the small square where the dot is, and then you've taken out the 2 rectangles.
Yeah. So you can think of this way. Maybe you think of this way. You see, you have a bigger one, and then you minus, you take out the 2 rectangles. But if you take 2 rectangles here, this area, you take twice. So you have to add up this area. So that's why you need to add this small rectangle. If you think out this way, maybe a bit easier.
Yeah, I understand.
Yeah, is that clear? Yeah, so that's a bigger one, large rectangle. And then you take out this rectangle, you take out this rectangle. So now here you have no loading, here no loading. And this one, because this one, small rectangle, the share by this 2 rectangles. So you take out twice. So you have to supplement this one. So you add the Q, add here. So it cancels out, it becomes 0, eventually becomes 0. That's why you add this one. Yeah. So if you still, so if anyone who are still unclear, then I can explain further.
Excuse me, sir.
Yeah.
So from what you say, so that means that the small triangle OZCT.
Yeah, OZCT. Yeah.
Yeah. So you say that equal to 2Q, and those 2 rectangle. Let me see. OSDT and OZBY will. Yeah. So like if I add two of those triangles, so that will have the small triangle OZCT, right? Is that? I mean, like it will equal, right?
I'm not quite sure I fully understand what you mean.
I mean, based on your formula you write down.
Yeah.
So the big triangle will be OSAY.
Yeah. That's the bigger one. Yeah.
Yeah, but I wonder like why do you add the OZCT?
You see, like I explained. So you see now originally you assume you add the Q. Originally OZCT there's no loading, right? Is that clear, right? So that will be this scenario. No OZCT, but in the beginning you assume there's a Q in this area. You assume there's a loading in this area.
So we assume that.
Yeah, you assume you add a Q because you try to use that Freedom design chart. So this all has to be the corner of all rectangles. So if you take a look, that's the corner of all rectangles. That's how it works. Otherwise, it doesn't work. So you assume you apply the Q for this big rectangle. So actually there's no surcharge or no load. So you have to take out the assumed part. So you take out this part and you take out this part. So now here that's become 0 and here becomes 0, which means no load. So that's reflect the real scenario. But here, if you take 2Q, then if you don't minus this one, it becomes negative Q. So you have to supplement. So you have to apply a Q, the surcharge, and do the calculation. And only in that way, it cancel out. So here, eventually will be no load scenario. And that will be the real reflection of the loading case.
Oh, all right.
Yeah. If anyone still unclear, then we can.
So if we say there's like this first one is 1, 2, 3, 4. Yeah. So in the formula you are saying that the 3 is equal to the altogether minus 2.
No. This is the 1, 2, 3, 4. Yeah.
No. The rectangle 1, 2, 3, 4. If we say rectangle 1, 2.
Oh yeah. 1, 2, 3, 4. Yeah.
Okay. So could you explain by 1, 2, 3, 4 with the formula that maybe we'll understand better?
So 1, 2, 3, 4.
Yeah. Yes. Now explain, please. Thank
you. So you see in the beginning, maybe we have to take the time. So in the beginning, originally you have only loading in 3. Is that clear?
Yes.
Yeah. So but the point O that's not inside, so you are not able to do the calculation straight away. So you have to try to form a shape that for O become a corner of the rectangle loading.
Yes,
that's why I formed shape 1, 2, 3, 4, right?
Yes.
But now because so this one I will get a value, right? Stress increase for this shape. So later on, because I know I add I take 1, 2, 4, but actually that doesn't exist. So I have to minus 1 and 2. Is that clear? Or 3, 4, maybe I minus 3, 4 first, 2, 4 first.
2, 4.
Yeah, 2, 4 is use right hand side, yeah. Up and down. So I take out 2 and 4.
Yeah. So actually, you out of this shape, you need to take 1, 2, and 4 off, isn't it?
Yeah. Eventually, you have to take 1, 2, 4 off. So let me maybe just do this way. Maybe quickly do this way. Maybe I can't. So 1, 2, 3, 4, right? So that's one corner. So that first, can you see that?
Yes.
Yeah. And then the next one, you have to take 1 and 4. You have to take out 1 and 2. So you take out 1 and 2. You becomes so you calculate 1 and 2 and you minus this one.
Yeah.
You minus 1 and 2, right?
Yes. And then 3, 4. Yes.
So because in this one, because in this time, this one O that's a corner as well. So the O that's one corner as well. And next time, you just calculate 1, 2, 3, 4. You calculate 2 and 4 and minus again. Because, so in this way, this one,
okay.
this one no load. Here will be no load, and here will be no load as well. But here you just count twice.
Oh, so okay.
You minus twice, so you have to just plus this one too.
Okay. So why are we doing this way? Like why we can't do one?
No. You have to make all that's a corner of all 4 rectangles. I explained.
Okay, so
times.
you need to make all corners all the time.
Okay,
I understand.
If I shade it, you see, if I shade it this way, always the corner of this this area, you do the calculation, you get one value. And all that's the corner of this area, and always the corner of this area, always the corner of this area. So
you consider all the time. Okay, understand. Yeah. Okay, thank you. Thank you.
Hope all the others be clear as well.
That sounds good.
Yeah. Let's continue.
That's clear.
Yeah. Okay. So this case, that's that case. For 18, for this example, the rectangular area ABCD is shown in the above figure, and we have the surface here. Now the Q is here. So Q, that's 100 kPa. We are required to calculate the vertical stress increase at point 1.5 meter below the point O. So it's here. So 1.5 meter. So that's the rectangular loading is here. Sorry. So that's the real loading area. When you have point O, is 1.5 meter. Sorry, it's 1.5 meter, and you have a point O here. So that's the case. So according to the previous slides, obviously we need to split into 4 rectangles, 4 small rectangles, and all the dimensions are already given in this figure. So according to the previous discussion, I think we all be very clear. Firstly, we construct a big rectangle, and then minus, take out this rectangle and take out this rectangle, and then add this one, because we minus this twice. So we have to supplement this one. So eventually we come up the value that's only for this real rectangular loading and for the stress increase for point O. So now let's do one by one. Again, for this rectangular loading OXAY, this big rectangle, we have the M. So M, that's the length of this rectangle. So that's 11 meter, 10 plus 1. And the width, that will be 2 plus 1. So that's 3 meter. So 11 meters, 3 meter. And the Z, again, Z, that's a constant. That's 1.5 meter. So we are able to easily work out the M, that's a 7.33, and N, that's 2. So now if we take N, that's 2, and M.
Sorry, sir, how we get like Z 1.5?
It's provided.
Question.
11.
It's given in the question. So 1.0, that's 1.5 meter below the ground. So that's given. And this 11, that's the long side. So 11, that's the long side of this big rectangle. Here you see 10 and 1, that's already provided. So
yeah, but why we didn't take it the 10 only?
10 only? No, 10 plus 1.
We're finding OXAY.
How are we doing for the like ABCD triangle?
No. Big rectangle.
The rectangle, yeah.
Yeah, big one. You see, OXAY. So we just calculate this big one. So this is 11 meter. This is 3 meter. Okay.
The pressure's from point O, isn't it?
Yeah. No. The pressure. We assume the pressure acting in this big area. No. But we calculate the stress increase at point O. Yeah. So now this time the N, that's 2, right? And we take N as 2. And M, you see, if I have the label M equal to 8 is labeled here, and M equal to 3 is labeled here. So obviously 7.33 is in a quite a narrow area. So we can find the intersection point somewhere here. And you draw the horizontal line, that gives you N sigma. So that will be 0.24. And N sigma times Q. So later on, I show you another, the Fathom chart by the other class. So according to this chart, N sigma times Q gives you the stress increase. So there's sigma ZZ. So that's for the first big rectangle, that's 24 kPa. Next for this small rectangle, so because it's a square, so B and L are the same. So it's all equal to 1 meter. And Z, again, that's a constant, that's 1.5 meter. So we can easily get the value of M and N, that's 0.67. And from this chart, we are able to take the value of 0.121. So here there's a log scale. So that's a 0.2, 0.3, 4, 5, 6. So that's where is 0.67 is. So again, S sigma times Q gives you the sigma ZZ, and for this small rectangular loading. So next, we just calculate stress increase for OX dt. So this time, again, the L will be 11 meter L. So B equal to 1 meter. So what we did, we just calculate the stress increase for this loading area. But actually, in real case, it doesn't exist. But we'll assume we have this pressure on top of this area. So only in this way, the O, that will be the corner of this rectangle. So now the M, that's 11 divided by Z and NB over Z. So again, we are able to find the S sigma from this chart. So that's 0.167. So if we do the further calculation, the stress increase is 16.7 kPa. So the final one, so the rectangular loading OZBY. So this time the L will be, obviously, L will be 3 meter. And this time B equal to 1 meter. So then we are able to calculate the M and N, so that the value is 2 and 0.67. So we take the value S sigma from the chart and we work on the stress increase for this assumed loading area. So that's 16.4 kPa. So finally, the stress increase at point O will be the stress increase for this big. So for this big rectangle, OX AY minus this one, OX DT, and minus OZBY, and then plus small rectangle OZCT.
Also.
So that's 3 kPa. Yeah.
So over here, to finding the loading OZBY, but over here it's OZC2. Is that a typo?
Yeah, I think that's OZBY. That's a typo. That's ought to be a typo. Yeah, right. OZBY. Maybe let me keep a note and just do the correction. Yeah. Okay. Sorry about that.
Yeah. All good.
Yeah. So one point you need to remember is that M and N are interchangeable. So either N is this is N or this is M value. It doesn't affect the result. The other one is that that's really important. You have to make sure the point, the corner, to get the corner of your rectangles to line up over the point of interest. So the corners, COR, corners of the corners of your rectangles to line up. So all the rectangles, they have to be lined up or share a single the point. That's the point. That's the point of interest over the point of interest. Currently, the point we are interested, that's the point O. So if you just you can do that, then you can successfully compute your stress increase for any cases, for any point that outside is a rectangular loading area. Okay. Now maybe we better just go ahead for another method. So previously we have learned the point loading, the circular loading for any point below the center line, circular loading for any point outside the center loading line, and also the rectangular loading and all different scenarios. Now there's another method to calculate stress increase, which is called the Newmark chart. So this is another design chart we are able to use to calculate the stress increase. The Newmark chart provides a graphical method for calculating the stress increase due to a uniformly loaded region or of arbitrary shape resting on a deep homogeneous isotropic elastic region. The chart allows the stress increase to be established by drawing the loaded area. So we could draw the loaded area to the crack scale. So according to this one, this will be the scale ruler. And note the length is OQ. And the loaded area should start from the correct relative position, which is the origin of the chart. So normally if you plot your loaded area, it's normally start from the origin of this chart. And the influence factor per block so this is the so-called per block. So influence factor per block equals to the scale factor equals to 0.01 should also be accounted. Now I will just demonstrate how the Newmark's chart is applied by way of an example. So here we have a uniformly loaded circle. So we have a circular loading area and it has a radius of 2 meters. So radius of 2 meters and Q equal to 100 kPa. So we need to calculate the vertical stress at 4 meters below the edge of the circle. So we have a circular loading area and its diameter that's 4 meters, radius 2 meters. So we need to calculate vertical stress. So it's the 4 meters below the edge. So let's say if edge is here, that's the 4 meters. So this one actually we can use the previous method, right? Circular loading and the design chart because that's not force on this center line. So we are able to work out the R and this is A. So we can use this method to do the benchmarking or double check the result. But right now we have to plot this circular area on top of this Newmark's chart. Maybe firstly, I need to give you some brief procedure for using the Newmark's chart. So firstly, we need to find the depth Z. So it's normally provided. So depth Z. So it's provided in this example, that's 4 meters. So at which the stress is to be determined. So Z is equal to the distance OQ. OQ is normally provided in this chart. So OQ. So OQ is just like confirm the length. So your Z, if your Z that's 4 meters, so that's your Z value. That's 4 meters. So for the other case, if you are required to calculate 8 meters below the edge of this circle, then this OQ equal to Z equal to 8 meters. So this length, that's the same, but the value, the representative value may vary according to the question. So that's what it means. And then we plot the loaded area to the scale because the OQ that's already confirmed. So we are able to plot the loaded area. So we need to plot to put the point of interest, which is the load increase beneath the edge of the circular load. For this example, at the origin of the chart. And also be aware of that the orientation of the drawing does not matter. So, which means we have to start from, because we need to, what we need to do, we just plot the circular loading area on top of this chart. But the radius or diameter has to be follow the scale of this one. So here, that's 4 meters. This length, that's 4 meters. And you know the radius, that's 2 meters, which means the D, that will be 4 meters. So D is 4 meters. And also this Z equal to OQ equal to 4 meters. So you know this diameter, that will be the same as this one. So you have to follow this rule to draw your circle. What means that direction doesn't matter means you are able to plot to the right-hand side, or you just draw a circle on top, or you draw a circle to right-hand side, doesn't matter. So eventually the shape, your shape ought to be the same according to this scale effect. And then next, we count the number of the squares or the number of blocks within the loaded region. So we only need to consider and count the squares with more than half of the area inside the loaded area. So finally, the vertical stress increase, the sigma zz equals to the number of blocks, effective blocks, I would say, times the scale factor, which is 0.001, times the surface stress Q. So it's normally provided. So which means once you plot this circular area, you count the block. You see, obviously, this block that's totally within this circular area. So we need to add this one. And then this block, you see, just only partially outside the circular loading. So we need to count this one as well. But for this one, you see, this block, the major, obviously, is over half of the area that's outside this circular loading. So we just ignore this one. We don't need to count this one. So we just count the number of blocks, 1, 2, 3, and count all the blocks, effective blocks within this circular area. That's the value of N, capital N. Okay, so capital N times the scale factor is normally provided 0.01 times surface stress Q. That gives you the vertical stress increase. So for this case, because the OQ that's equal to Z, so OQ equal to Z equal to 4 meter, and the radius R that's 2 meter. So we know the diameter is 4 meter. So the diameter of this circular loading, that will be the same as this length. So for the other case, if the diameter that's 1 meter, if the radius that's 1 meter, then the diameter of your circular loading, that will be 2 meter, right? So diameter will be 2 meter. But you know the length here, the OQ equal to Z, that's 4 meter, that's the length. So you have to plot your circular loading half. That will be the half of the length. Because you know this one, that will be the 2 meter diameter. So that's how you plot this circular loading area. And then you count the number of blocks. So if we count this one, the blocks will be 194. Just another ones. So if you count the blocks within this circular area, that will be 194. So if actually that's because that's symmetric, so you are able to only count the half of the circular area, and then times 2, that gives you the value. That should give you the same value. That saves you half of the time. So that's normally what people did. You just count half of the circle and times 2. So this N times scale factor times Q, that's a stress increase. Because we have referred as this is a circular loading problem. So refer to the previous slide. The Z equals 2, right? Z equal to 4 actually. So we have circular loading. At depth of 4 meter. So Z equal to 4 and A equal to 2 meter and R equal to 2 meter. So that's what we learned for circular loading, right? So Z over and Z equal to 4 meter. So Z over A, that's 4 divided by 2. So that's 2. R over A, that's 2 divided by 2. So that's 1. So if you know Z over A and R over A, refer to the previous design chart, we are able to find the influence coefficient. So that's 0.2. So 0.2 and sigma times Q gives us the stress increase. So that will be 20 kPa. This is quite close to this value. So which means both methods are valid. So either based on the Newmark's chart or based on the circular loading area and design chart method, we get the similar result. Both are valid, correct. So that's the Newmark's chart method.
Can you just explain where the 0.2 came from?
That's from the design chart of the circular loading, our circular loading.
Okay.
Yeah. This will be our final method. So this is another approximate method.
So I have a question. Can you go back a little bit? You said that we multiply this the 0.2 times Q.
Yeah.
Well, how do you get Q, or what's Q given?
No, Q here.
Yeah. So 0.2 times 100.
Yeah.
All right.
No, this is for the previous few slides. Maybe you want me to go back.
I remember how to
Yeah.
calculate.
I don't want to go back just in case I lost.
Yeah, my question was how you got the
Q is provided. So you see this one, that's same as this scenario. You see?
Yeah.
This is the chart you get as sigma. Yeah.
Excuse me, sir.
Yeah.
About N. So for example, like you say, we have OQ is 4 meters. So like how we calculate all square block in that circle, right?
Yeah.
So we got 194.
Yeah. So no, you can count the half of the circle.
Half
of the circle. So maybe this one just a bit maybe quite typical question. So like I explained before, so if this OQ that's provided on the chart, so that's a constant. This length that's a constant. Okay, this OQ that's a constant, and this OQ if your J that's given, so this OQ equal to J, so J is the depth equal to whatever the value.
4 meters.
So 4 is this case, yeah. So it's 4 meters. Let's say because J that's provided, so that's 4 meters, right? So let's say if I change circular load, that's currently that's 2 meter load. How about there's 4 meter load circular loading? How you draw the plot? So 4 meter, radius of 4 meter, which means the D equal to 8 meter, right?
Yep.
Yeah, D is 8 meter. But this is the scale ruler, SCA scale ruler. This is this J equal to 4 meter. That doesn't change at all. But your D is 8 meter, so you have to plot this length relative to this one. So which means the diameter will be doubled on this chart. Is that clear?
Yeah.
Because this one, the J and OQ, that's 4 meter. Your D is 8 meter, so it should be this length. So roughly here, right? So now your circular loading area will be this one.
Yep.
So that corresponds to the circular loading with the radius of 4 meter or diameter of 8 meter. And then you just, so you can double check this diameter will be the double length of this OQ. Okay. And then
would N end up being double?
No,
it doesn't work like that.
Yeah, it doesn't work that way because you see it you see close to the center is a bit dense area, further away from the center is a bit coarse, so it's not uniform shape. So it doesn't. You can't count that way. So eventually for the D equal to 4 meter loading area, that circle loading area, you have to recount again. But what you need to do, you just count half of the circle. You see either this one or this one, and then times 2. Yeah, double it. Yeah. So you see, obviously for this block, you don't need to account for it. Use the majority of the area or over half of the area that's beyond, that's outside this circular loading area. Okay, and this one that's the same, and this one you have to account that one. So you have to add that one to N.
So it's always the ones that are more than half.
More than half.
Yeah.
So you see this one you have to ignore, and this one you have to account. You see this one, this block.
Yeah.
And this block you have to ignore. Yeah. Okay, is that clear? I think we have more particles for this one. You see, we just vary the radius circle loading from 1 to 2 meter or to 8 meter. And then just your circle either shrink or enlarge, and then you count the number of the blocks. Is that clear?
Yeah, thank you.
Okay. So now we just go to the another approximate method, which is called the simplified 2-to-1 method. This is a very rough method to calculate the stress increase. And also this is for rectangular loading actually. So this is, again, this is a side view. So this is B. So you have the B here, you have L here. This is a rectangular loading. And if that's the ground, you have the surcharge. Q. It assumes the stress will just transfer further to any point underground at the constant ratio, which means the loading is assumed to be dispersed at 2/1 rate. All the stress distribution along the line with 2 vertical to 1 horizontal line. You see that's vertical, that's 2, and horizontal 1. So that's the ratio. So that's the assumption of this 2-to-1 method if you have the circular loading. And then if you are required to calculate any point in this level, then we have this formula. So at the depth J, so J that's this level. At depth J, the stress increase. The area now becomes, so because it's enlarged at 2-to-1 ratio. So the length becomes L plus J and the width becomes B plus A. So now the area becomes B plus A times L plus A. And the Q again, so the force equal to, so we know the force equal to Q times area and equals Q times area, that's a B over L. And the force divided by area gives us the pressure or sigma. So that's the definition. And now, because we are required to calculate the stress increase at this point, so we need to use the corresponding area. So this area will be B plus A times L plus A. So it will be QBL divided by B plus A times L plus J. So some points we need to consider for this simplified 2-to-1 method. So because P, L, and B are constant, so with the increase of the depth, so if Q that's constant, and B and L both are constant, so the more you increase the J, so which means the deeper the point is, then the smaller the stress increase. So that's what it means. And also it's a very crude method to distribute some sort of load down through the soil at the slope of 1 horizontal to 2 vertical. So all we are assuming is that the soil particles are distributing these loads out so that the deeper we go, the broader that the cross-section area becomes. And this approach is super easy and it tends to be conservative, meaning that it's going to predict larger stresses than actually exist in the soil. So which means we have some safety margin. That's the so-called conservative. We want to predict a bit higher than it should be, because so in that way, in the design, we will keep some safety measures or safety margin. So it's just something if you want to really quick check yourself during the preliminary analysis. So because of the conservativeness in the predicted stress, it's not good for any settlement analysis. So those are some points for your information. And this is our last example of
Excuse me, sir.
this class, yeah?
Like the point of the loads should be under the rectangular area, or it could be outside for this with this method.
So this method is mainly just mainly maybe within this this rectangle, the enlarged area. But this will be very rough, quick calculation. This one. So this is a last example of this class, and is to use the simplified 2-to-1 method to calculate the stress increase. So we have a 3 by 5 meter rectangular area, and carrying a uniform load Q is 240 kilonewton per square meter applied to the ground surface. We are required to calculate this vertical stress increment due to this load at a depth of 6 meters below the ground surface by this simplified method. So from the given condition, we know it's all given condition, the Q, B, L, and Z. And we can easily work out the P or the force equal to Q times B times L. So that's 3,600 kilonewton or 3.6 meganewton. And then we plug in this value to this formula. So we know B, L, and Z. We can easily work out the value of stress increase as 36.4 kilonewton per square meter. That's a quite easy example. And finally, I'd like to just provide a summary of the stress increase, what we have learned from this lecture. So for point load, we use the Boussinesq. So if you have any point on the ground, we have a Boussinesq analytical solution to calculate the stress increase. So any point below the ground at point A. So we are able to refer to that formula to do the calculation. And then for the circular loading, and any point below the center of the circular loading. So we have a circular loading, and any point below the center of the circular area, we are able to use another analytical formula, which is the integration of the previous point loading formula. We are able to refer to that formula to do the calculation to work out the stress increase. And we also have another scenario. So that will be again, the circular loading. And for any point that's not on the vertical line. So another point will be, so we need to work out the radius A for the circular loading, and also the radius R for this B to this vertical loading line, and then refer to the design chart or the influence chart to find the influence factor I sigma. So, and then our stress increase per sigma ZZ equal to I sigma times Q. So that's the second scenario. So 2 scenarios for circular loading. And then for circular loading, we have another method, which is called the Newmark's chart. So that's one. Normally the chart will be provided. So firstly, you just find the length OQ. This OQ normally is already drawn on this chart. So the length is fixed, and this OQ equal to Z. So if Z is 4 meters, then this OQ equal to 4 meters. If Z is 10 meters, then this length equal to 10 meters. So that's just a relative ruler or the scale you need to follow to draw your Newmark's chart. So to draw your loading area. So normally this one is used to draw your circular loading. So normally you have to start from the center of the Newmark's chart, and then draw your circular area. But firstly, you need to find your diameter relative to this OQ. So if your diameter is the same as the depth, then obviously you use that scale, this OQ scale, and that's the diameter. Draw your circle shape. So it's either So as long as the first point that's lands in the center, so it's either you draw in the right-hand side or to the left-hand side, doesn't matter. It doesn't affect your result. Then you just count. Then you just take a half of the circular area. And for any boundary block, be careful. So you just count the area. Has to be the half of the area within this circular loading. Otherwise, you just ignore that one. Then you are able to count the number of n for this half circular area. Maybe I call it n1. So n1 times 2 because it's in symmetry. So and then that's the number of blocks. So n, the number of blocks times scale factor, normally 0.01 times q gives you the stress increase. So that's the Newmark's chart we have learned. And then for the rectangular loading, so this is really important. I have to stress or highlight again. This is a really important part of this lecture. I think there will be lots of assessment relate to this one, Pfeiffer's design chart. In total, we have 6 scenarios, but all the other 4 scenarios are really are quite simple. So you normally for the scenarios 3 and 6 are the most important ones. So 3 is any point that's not in the geometry center of this rectangle. So if it's here, if the point is here, somewhere below the rectangular loading, then you just draw a vertical line and horizontal line and break it into 4 small rectangles. So in this way, this point, you see that's the share between all 4 rectangles, 1, 2, 3, 4. So that's the corners of all the rectangles that you created. Then you just work out the stress increase separately and sum them together. So that's for the case 3. So case 3. And case 6 is your point that outside is the rectangular loading area. So what you are trying to do, you have to form the rectangles all the time. But this point has to be the corner of all the rectangles you created. So firstly, you just create a big rectangle and then calculate the stress increase. Because but here, actually, they have no pressure or no stress. So you have to take out this one. And here you have no pressure or stress. You have to take out this one as well. But this part, you minus this one twice. So you have to plus this one. So in this way, you see this point that's what's shared by all the rectangle shapes you form. So here you have to be careful. This point has to be the corner of all the rectangles you created. Only in that way, you are able to use the Pfeiffer chart to do the calculation. And that's the case 3 and case 6. That's really 2 really important cases. And finally, we have the rectangular loading case. This is a very rude or very rough method to calculate the stress increase. There's sigma ZZ equal to QBL. So normally, you know the length and width, you know the Q divided by B plus Z times L plus Z. So this is a rough method to do the calculation. So that's, I think that's all the method we have learned from this lecture. So by now, maybe I would like to take a chance to maybe find, let me see whether the browser works, to find the design chart, the Pfeiffer design chart that you are going to use for your calculation. Can you see the screen now?
Oh, yes, working. Yeah.
You see in the view set, you have a useful information. This one contains, that's in the learning module section. So this one contains all the formulas you are going to use, either for the quiz or final exam. So that's a summary I already created for you. So this one I try to find how to. This one, you see? Can you see this one? That's actually that's the equivalent figure you are going to use in any assessment. I recommend use this one. This one is equivalent to the Fider's chart. So you see in the left-hand side, the axes are clearly labeled. Is that right? You see 0.18, 0. So this will be 0.19.
Oh yeah, that's more accurate. Yeah.
Yeah, 0.19 and 0.21.
That's more easier
right?
to read.
Yeah, and also if you look at the chart, the lines, so the horizontal axis, that's n, and those lines, obviously that will be m. You see, that's m equal to infinite, and m equal to 3, and 2.5 is all labeled on the chart. So you can do your own interpretation. I think this is very clear, right? I think you all agree on that. So you just use this one, this chart, to do the calculation.
How the chart above, sir?
Huh?
How about the chart above? Oh, okay, yeah, no, that's good as well. Yeah,
this is good as well. You see, this one just only is for circular loading case. This is for rectangular loading.
Yeah.
And this use this one. This will be probably won't be provided, but you can find this one from our view set. Use this one to to calculate stress increase. Okay.
So, I'm a bit confused on how to draw the diagram of the Newmark chart. Like, I understand that to draw it to scale, but I'm a bit confused on how to draw it to scale. Like, do we use like a ruler to measure outwards?
Yeah, I think so.
Yeah.
I think you have to use a ruler. So you have normally if you are required to do this one. So this figure will be obviously provided. So you use a ruler to measure this length of Q.
Oh, so it's like so 1 centimeter equals to 1 meter. Is that the scale?
So what's the text you written?
Oh, so it's like so 1 centimeter on the ruler is equal to 1 meter in real life. Is that the scale?
No. It's not synced that way. So this one, the OL. So this one that's fixed. That's provided. That's fixed on the on the papers. So it doesn't matter. So if your Z, so it only has a correlation with your depth Z. So if Z is 1 centimeter or Z is 10 meter, it doesn't matter. So it just equal to this Z. So if Z 1 centimeter, this length is 1 centimeter.
Yeah.
If Z 10 meter, this OQ is 10 meter. But this one just only correlate to the radius of your circular loading.
Yeah.
If your radius or diameter, if your diameter is 10 meter, then this OQ will be same as your diameter. Yeah. So if your radius is 5 meter, if your radius is 2.5 meter, then which means then you will have to draw the half the circle. Because here there's a 5 meter. Okay.
Yeah. Wait. Yeah. So we're given this value, like we're given from there to there. That's given.
Yeah, that's given. That's a plot on the chart. That's normally given.
Okay. So what we do is just plot the circle by using from that point to that point.
Yeah.
Okay.
Using this scale.
That's more easier. Yeah.
This is a so-called scale. So you have to make sure this diameter is the same as this one, or just in proportion to this length. So either in proportion or the same.
Yeah. So
but you have to make sure you draw a circle. It has to be
in a region.
Roughly a circle. Yeah, reasonable. It can't be an irregular shape.
Yeah. What we do to basically like go down here, right? Like then after that we draw the straight line down there and one straight line down here. Then we can draw a circle based upon those two lengths, like that basically. And then we can
for this case you can do this way, but for the other case, like I said, how about the radius? That's 10 meter. Then it doesn't work out that way. Then you have to maybe firstly you just draw a length. You see, draw a length in proportion to this one.
Yeah.
So if your length that's 8 meter, I mean your diameter is 8 meter, and Z is 4 meter. Then you draw a line that's double this one. That will be your diameter, and then you just maybe find another one, maybe another point that's through the center point, and then you draw another line, which will be this 4 meter.
Yeah,
okay?
to draw it then basically,
yeah,
you
and
move
then
it to the other side. Yeah.
Yeah. So you find maybe a few critical point and then maybe connects roughly with a circle.
Yeah.
Yeah. Okay.
All right. Thank you so much, sir.
Okay.
Hey sir, can you go back a few slides? Because there's something I don't quite sure.
Which one?
A bit more. I think it's on this slide. I think it's on the bottom right. Yeah. One more. Yeah, that one. The delta.
ZZ. There's sigma ZZ. Yeah.
Yeah. Yeah. How do you get those numbers?
No, those you see those numbers are the mathematical sum of all the rectangles. So previously we've already discussed multiple times. So that's the value from the previous calculation. This is only for this rectangle, OZBY 16.4. Here, you see, you have to minus this value, the value from this OZBY, and you have to minus the value for the OX DT. You have to plus the value for the small rectangle. Yeah. Okay.
Can you? Sorry. Yeah, back to where we were just looking. Yeah, that one. Just explain which ones represent. Well, I can see that that's 1.5, which is correlating to which number on the top.
No. You see here, you see maybe, so that's why, but in the assessment, we don't use this chart, but here that's 0.15. So right, that's 0.16.
And what's it connecting to the top? What number is that?
This one?
Yeah, above 0.6.
0.
The red line.
This one? So you see, this is 0.15, 0.16. So that's 0.17. Obviously, it's roughly in the middle of 0.16, 0.17.
Okay.
So that's 0.164. But if you take 0.163 or 6 or 7, that's all be fine. Because we can't be that accurate from our naked eyes.
You're talking about the numbers from M and N.
So as long as your first two decimal numbers are correct, then that ought to be fine. No, here, I sigma. So I sigma.
How do you get that I?
Huh?
How do you get that value there? 0.164.
Yeah. So that's in the middle.
Do you just look at the graph?
Yeah, you just look at the graph.
All right.
Okay. So here, this is 0.15. So this is 0.16. And this is 0.17. So here, obviously, this red arrow is roughly in the middle. So that's why I get 0.164.
So, are we meant to subtract that plus 16.4 because it's OZ?
No. You have to, you see, we discussed multiple times. You have to minus this one. This error doesn't exist. So you have to minus this one.
But it's OZCT. Are you meant to add that one?
No. This is a typo.
Oh, okay.
Or should be OZBY. I will correct later on. Yeah, OZBY. OZBY.
So those two lines are referring to 2 and the 0.67.
Yeah.
And then you're getting the I. Okay, yeah, understood. Thank you.
No. This represent 2 and 0.7. Yeah, and then you get 0.164. Yeah, that's right.
Yeah.
So for all the other cases are the same.
Okay.
Yeah. One line connects M, and the other line just connects to the I sigma, but they intersect. So hopefully, you see how these approaches can be very useful and powerful to allow us to calculate the stress increase when we apply different types of either point or circular or rectangular loading. I think that's the end of our lecture today. You're going to have a fun time practicing these methods in our tutorial class. If no other questions, then I have to close now.
All right, see you Thursday. Thank you.